Hello everyone. I welcome you all to this 14th lecture of Structure of Atom. So myself, Varad Daoo, I am a doctoral student at the Department of Chemical Engineering, IIT Kanpur. Okay. In the previous class, we have seen about different quantum numbers, right? Principal quantum number, azimuthal quantum number, magnetic quantum number, and spin quantum number. We have also studied about their symbolic representation, and we have also studied about in detail about what each quantum number stands for and how by with the help of these four quantum numbers we can uniquely determine or describe the electron, right? And we have also seen the maximum and minimum values of this quantum numbers, right? So in today's class, what we are going to see is we are going to see about the shapes of these orbitals, right? In the previous class, we have discussed about difference between orbits and orbitals, right? And then we studied about quantum numbers. And in today's class, we are going to study about how these electrons are distributed in this orbital and orbits. So we are going to study some principles, right? So first, what we are going to study? First, we are going to study about the shapes of the orbital, right? The first topic is going to be the shapes of atomic orbitals, right? Shapes of atomic orbitals, right? So it has been learned that the probability of finding the electron does not become zero even at large distances from the nucleus. Therefore, it is not possible to draw any sort of geometrical figure that will enclose a region of 100% probability. However, for the sake of pictorial clarity, we draw figures in which the probability of finding the electron is maximum. And these most probable regions are called as boundary surface diagrams or orbitals, right? The first point which we are going to write is it has been learned that the probability of finding the electron does not become zero even at large distances from the nucleus, right? Hence, what we do is we draw figures in which hence we draw figures in which the probability of finding the electron is maximum. Right? It is about 90 to 95%, right? And these most probable regions are called as boundary surface diagrams or orbitals. Orbitals. Right? So we are going to the first topic in this we are going to study about radial wave function. Right? So the shape of our orbitals are determined from the variation of wave function, that is psi, as a function of r. Right? Shape of orbital is determined with the help of psi and r plots. Right? These are called as radial dependence or radial wave function, and these plots are called as radial wave functions. Right? The right. So these graphs are like this. So an example of these graphs could be like this. Where right? Where this is psi. Right? This is the shape of 1s orbital where L is the 1, L value is 0. This is psi. This is R. Right? Let us call it as figure A, figure B, figure C. Right? This is psi versus R. Right? This is 2s orbital. L is equal to 2, L is equal to 0. Right? This is 2p orbital. n is equals to 2, n is equals to 1, right? These are plots of wave function with distance from the nucleus, right? So this graph shows the 1s, 2s and 2p orbitals, right? It is clear from this figure, this way that the wave function for 1s orbital continuously decreases with increasing r, where however for 2s orbital the wave function increases in the beginning with increasing r and then becomes zero at a particular distance, and this is called as node. Hmm, right? The wave function decreases in the beginning with increasing r, becomes zero at a particular distance and then becomes negative. And the wave function for 2p orbital first increases to a maximum and then decreases, right? So it is very interesting to know that 2s wave function can be positive or negative, right? Here it is positive, here is it negative. Depending upon the distance, it may be noted that the positive and negative signs refer to the signs of the wave function and have no connection to the positive and negative charges, right? So this point has to be written down, right? It has to be noted. Figure B, that the positive and negative sign I of r refer to the sign of wave function, sign of the wave function, and have no connection to the positive and negative charges. As we have seen for this 2s orbital, right? As we have seen for this 2s orbital, at a point the wave function becomes zero, right? Here the wave function becomes zero, right? Here the wave function tends to zero. The point at which the radial wave function becomes zero is called as radial node surface or simply a node, right? This point also has to be written. The point at which radial wave function becomes zero is called, right? At the node, the value of the wave function changes from positive to negative. In general, it has been found that ns orbital have n minus 1 nodes. Similarly, np orbitals have n minus 2 nodes, and so on. The value of wave function changes from positive to negative, right? So in general, ns orbital has n minus 1 nodes. Similarly, np orbitals have n minus 2 nodes, right? Where n is the value of the orbital, right? In all cases, psi approaches 0 as r approaches infinity, right? As r approaches infinity. Right? It may be noted that like psi, the plots of psi also do not have physical meaning, right? However, the importance of this plot lies in the fact that they give information about how radial wave function changes with distance and about the presence of node where the sign of psi changes. And this is particular importance in understanding the chemical bonding, right? So part B is going to be probability density graphs. What is probability density? It is nothing but psi square, right? So according to German physics, Max Born, the square of the wave function gives the probability density of finding the electron at particular point. Probability density of finding the electron at a distance of r from the nucleus. The chi-square plot for the figures which we have seen, right, in the previous class. In this, so this is the psi value, right? So this is the psi versus r. Now we are going to plot the same for psi square versus r, right? Psi versus r, and we are now going to plot the similar for psi square r. This is going to be like this. This is psi square versus r. This is going to be like this. This is psi square. This is figure A, figure B, figure C. This is r, right? This is psi square, right? And this is going to be the node. This is the plot of 1s orbital, 2s orbital, and this is 2p orbital, right? So these are the variations of psi square as a function of r, right? Obtained by plotting psi square versus r. The plots are for this 1s, 2s, and 2p orbitals, right? These diagrams look similar to these diagrams, right? To this diagram, except that the because the square has been implemented, the negative side of this plots has been gone to upper side, right? These graphs are called as probability density graphs. It may be noted that for s orbital, the maximum electron density is at the nucleus, and for p orbital, it has zero electron density at the nucleus. It may be noted that all orbitals except s orbitals have zero electron density at the nucleus, right? So these graphs are called as, may be noted that for s orbitals, maximum electron density is at the nucleus, and for p orbitals, it has zero electron density at the nucleus. Right? It may be noted that all orbitals except s orbitals have zero electron density at the nucleus. Right? The next topic which we are going to study is radial probability function, which is nothing but 4 pi r square psi square, right? Hmm. So psi square versus r plots gives the probability density for the electron around the nucleus. However, in order to determine the total probability of an infinitesimally small distance, we have to multiply the probability density by volume of the region, right? So in that case, is going to be probability is going to be, right, which is nothing but psi square into dv. That is the volume of the differential region. Is the volume of differential region, right? Since the atoms have a spherical symmetry, it is more useful to discuss the probability of finding electron in a spherical shell between the distance of r plus dr and r. To understand this, right? So let us try to understand this. Right? So what we have is, so what is the value of this dv? That is what we are going to find out. Right? So let us consider these are the values. So its radius is going to be r, and this is going to be r plus dr. Such that this distance is dr. Right? So volume of the shell, right? So volume of this shell, that is going to be what? Right? This is going to be 4 by 3 pi r plus dr cube minus 4 by 3 pi r cube, which is nothing but 4 by 3 pi. We are going to take constant, r plus dr cube minus r cube 4 by 3 pi r cube plus dr cube plus minus 3 pi r dr, sorry, it's going to be, right, this is going to be 3 r dr multiplied by, or in other words we can write this as plus 3 r square dr plus 3r dr square, right, minus r cube. So cancelling out this term and this term, we are left with 4 by 3 pi dr cube plus 3r square dr plus 3r dr square, right? But dr is very small than r, hence dr cube very small than r cube, right? Hence neglecting term with dr cube. Similarly, dr square is very less than r square, hence neglecting term with dr square dr square, right? Hence what we get is this is going to be dv. So we are going to neglect this term, right? And also this term. So what we end up with, this is nothing but 4 by 3 pi into 3 r square dr, right? Hence dr is going to be 4 pi r square dr, right? And this is what we are going to include in this expression, right? And when we do it, what we get is, we get the probability is nothing but pi square dv, pi square into 4 pi r square dr, which is nothing but 4 pi r square dr into psi square, right? Right? This is very important expression, right? This gives the total probability of finding the electron at a particular distance r, and this is also called as radial probability. Right? The plots of probability as a function of distance from the nucleus are called as radial probability distribution function, right? Or RDF. Let us write this down. So this gives the total probability of finding the electron at a particular distance r, right? This is called as radial probability, right? And the plots of probability which is nothing but 4 pi r square into psi as a function of distance from the nucleus, which is nothing but r, is called as radial probability distribution function, right? It is clear that the radial probability distribution function graphs depend not only on the probability density but also on the volume of the shell. The probability density, that is the psi square for 1s, is maximum at the nucleus and it goes on decreasing with distance, right? However, the volume of the shell goes on increasing with increasing distance, right? The product of probability density and the volume of the shell gives the radial probability distribution function, right? So we can understand this from these plots, right? So this is the plot. Let us assume this is what psi square versus distance is r, right? And this is what is I square. So this plot is of psi square, right? Psi square, right? And if we plot on the same graph, so this is going to be the volume, right? This is the volume of the shell, right? What is this going to be? This is going to be distance in r, and this is going to be probability, right? Probability, which is nothing but 4 pi r square into psi square, right? So this is going to be like this. This we are drawing for, right? Radial probability function function for 1s orbital, right? So from this, what we can see is that from this we can see that the probability density psi square of 1s is maximum near the surface, right? Is maximum near the nucleus, and it goes on decreasing with distance. However, the volume of the state goes on increasing, right, with increasing distance. The product of probability distribution, right, probability density and the volume of the shell gives the radial probability. This is the radial probability, and its product against the distance. So it reaches maximum and decreases, right? So this graph for 1s orbital shows that the probability of finding the electron is zero at the nucleus, and it keeps on increasing and becomes maximum at a particular distance from the nucleus, right? The peak of the curve gives the distance from the nucleus where the probability of finding the electron is maximum, and this is called as radius of maximum probability, right? For hydrogen atom, this distance is found out to be 0.529 angstrom, and this value agrees well with the value calculated by Bohr, right? However, it is important to note that the Bohr predicted that the electron will always be at R equal to 0.529 angstrom for hydrogen atom. However, according to wave mechanics, the probability is most likely to be found at this distance, but there is a probability of finding the electron at a distance shorter and larger than this value, right? So we should write this down. So from above graphs, what conclusion we can draw is the graph shows that the probability of finding the electron of finding the electron is zero at nucleus, right? It keeps on increasing and becomes maximum at a particular distance from the nucleus, and then gradually decreases, right? The peak of the curve gives the probability of finding the electron, right? Distance from the nucleus, where probability of finding the electron is maximum, right? And this is called as radius of maximum probability. Right? For hydrogen, this distance has been found out to be 0.529 angstrom, right? And this value agrees well with the value calculated by Bohr for the radius of first orbit, right? However, it is important to note that Bohr predicted that the electron will always be at r is equals to 0.429 angstrom, right? For hydrogen atom, right? However, according to wave mechanics, the electron is most likely to be found at this distance, but there is probability of finding the electron at distances shorter or larger than 0.429 angstrom, right? So this is very important. So now we are going to plot the probability distribution functions for plots of probability distribution function versus r for various orbitals, right? So this is nothing but 4 pi r square psi square r, right? 4 pi r square psi square r, 4 pi r square psi square r, where this is the distance. This is what? This is our figure A, this is our figure B. This is figure C, and the whole figure is called as radial probability functions as a function of distance r from the nucleus, right? And this is for 1s orbital, this is 2s orbital, and this is 2p orbital, right? Right. So next what we are going to study about is boundary surface diagram, right? Let me drag a picture. The shapes of the orbital may be represented in terms of boundary surface diagram, right? So in this representation, so we'll do it afterwards. So in this representation, a boundary surface or contour surface is drawn for an orbital on which the value of probability density is constant. In principle, many such boundary surfaces may be possible. However, for a given orbital, only that boundary surface diagram of constant probability is taken to be good representation of the shape of the orbital, which encloses maximum probability density, right? So what is that we are going to try, right? The shapes of orbitals may be represented in terms of boundary surface plots, right? So this is the boundary surface diagram of 1s orbital, right? So s orbitals are non-dimensional and symmetrically spherical This means that the probability of finding the electron is same in all direction at a particular distance from the nucleus. So this is the fixed representation of 1s orbital, right? 1s, this is 2s orbital, and these are the directions, the coordinate axis, right? In this observed that the density of charged cloud is maximum at the nucleus and decreases with increase in distance from the nucleus, right? This is the region of zero probability, which is also called as node, right? So 2s, so 2s orbital is also non-directional, right? And spherically symmetrical. In this case, the probability density is maximum at the nucleus and becomes small at larger distance. However, the effective volume or size of 2s orbital is larger than 1s orbital. An important feature of 2s orbital is that there is a spherical shell within 2s orbital, right? This spherical shell, where the probability of finding the electron is practically zero, right? This is called as a node or nodal surface, right? This is called as a node. Thus, a 2s orbital differs from 1s orbital in being larger in size and having a nodal surface, right? So now we are going to study about the shape of. So we are going to add on the next figure, which is the 2p orbital, right? P orbitals. So these are the 2p orbitals. No, no, this is not the page trash, right? So we are going to find the image, right? So this is the figure, right? So this is the 2px orbital, 2py orbital, and 2pz orbital, right? So as you guessed, right, x stands for the direction in which orbital is presented. It is of dumbbell shape, right? So this is y-axis, hence y. This is z-axis, hence z. For p orbitals, right, there are three possible orientations corresponding to ml equal to, so three possible orientation for p orbitals for each for ml equal to -1, 0, and 1, right? This means that these are the three orbitals and three positions, right? So this is what we are calling px, this is py, and this is pz, right? And this representation is this, its representation is this, and its representation is this, right? So these three orbitals are equal in energy but differ in their orientation. Each orbital consists of two lobes symmetrically spaced about a particular axis. Depending upon the orientation of lobes, these are designated as 2p or 2px, 2py, 2pz, right? So this is 2px, 2py, 2pz. Accordingly, as they are symmetrical about x, y, and z axis representatively, respectively. 2px or that is 2px orbital has two lobes symmetrically spaced around x axis, 2py around y axis, and 2pz around z axis. The shape of the orbital is called as dumbbell. Right? Shape is called as dumbbell, right? Right. So now we'll go study about the nodal surface, right? For this also we are going to drag a figure. Okay. So it may be noted that two lobes of the p orbital are symmetrically placed around a plane having zero electron density, and this is called as nodal plane, right? So this right here is a nodal plane for 2px. This is 2py, a nodal plane for 2py, and this is nodal plane for 2pz, right? So it should be noted that the probability of finding the electron in a particular p orbital is equal to both the lobes, right? The p orbital of higher energy values have similar shapes, although their sizes are bigger, right? So 4p is going to have larger size than 3p, which is going to have larger size than 2p, right? Okay. So now we are going to go on to the next topic, right? Which is the shape of the d orbitals, right? So these are the shapes of d orbitals, right? This is dxy, this is dyz, this is dzx, this is dx square minus pi square, and dz square, right? For d orbitals, L is equal to 2, right? For d orbitals, L equal to 2. That means minus 2, minus 1, 0, ml values 1 and 2. Right? So there has to be 5 orbitals, right? So this corresponds to 2, minus 1, 0, 1 and 2. Right? And these are the boundary surface diagram, right, of 3D orbitals, right? So now we'll move on to the next topic, right? It is the energy level diagram for electrons, right? For this also we are going to drag a figure, right? Right. So the relative energies of various orbitals can be shown by arrangement known as energy level diagram, right? Let me write this down. The relative energies of various orbitals can be shown by an arrangement known as energy level diagram, right? It is clear from the figure that the energies of various orbitals in hydrogen atom depends only upon the value of the principal quantum number and independent of value of n. Right? In other words, all subshells of given in the principal shell have the same energies. Right? So this is one. You know, given principal shell have same energies. Right? So the order would be 1s less than 2s, which is equal to 2p, 3s equal to 3p, 4s equal to 4p, 4d, 4f, right? So on and so forth. Right? Although the shapes of 2s and 2p orbitals are different, an electron has same energy when it is in 2s orbital or when it is in 2p orbital. The orbitals have the same energy are called as degenerate orbitals, right? And the electron in 1s orbital is called as is in the most stable state and is called as ground state electron. Right? Right? So what we are going to study about now is we are going to study about the of Bau's principle, right? What does this principle tell us that about principle? So what does this principle tell us that? It says that in the ground state of an atom, an electron enters the orbital of lowest energy first, and the subsequent electrons are fed in the order of this principle states that in the ground state of an atom, an electron enters the orbital of lowest energy first, and subsequent electrons are fed in the order of increasing energies. The word Aufbau in the German means building up, right? Right. So according to above principle, the orbital should be filled in above sequence, right? So the sequence in which it should be filled is 2s, then 2p, 1s, then 2s, then 2p, 3s, 3p, 4s, 3d, 4p, 5s, then 4d, then 5p, 6s, 4f, 5d, 6p, and 7s, right? It is very important to remember that the sequence of energy levels pertains to 3p and then 4s orbital, right? Right. So in order to explain this, right, so what we can do is You can drag a picture, right? So this is the way the electrons are going to. So you can remember it like this. So first 1s you can write like this is 1s, then 2, then 3, 4, all the orbitals in first orbit, second orbit, third orbit, fourth orbit, so on and so forth, right? And then you draw an arrow like this. So first it is going to be 1s, then it is going to be the 2s orbital which is going to get fixed, then it's going to be 2p, and then 3s, right? Then it's going to be 3p and then 4s. After 3p it's not 3d, it's 4s, right? Then 3d, 4p, 4, 5s. Like this you have to continue. So this is the schematic diagram to remember the sequence of filling atomic orbitals, right? So the next is Hunt's rule of maximum multiplicity, right? So what does this rule tells us that? According to this rule, electron pairing will not take place in the orbitals of same energy until each orbital is singly filled, right? Electron pairing will not take place in orbitals of same energy, that is nothing but same subshell, until each orbital is singly filled. So this suggests that it is difficult for an electron to enter an orbital which already has an electron than to enter an unoccupied orbital of the same energy, right? So this suggests that it is difficult for an electron to enter an orbital which already has an electron than to enter an unoccupied orbital of same energy. Unoccupied orbital. This is to be expected because there would be some repulsion between the electrons since their charge is same. Right? So this principle is very important in guiding the filling of p, d, and f orbitals, right? Which have more than one kind of an orbitals, right? Right. So last one, the topic which we are going to cover is the Pauli's exclusion principle, right? So as per Pauli's exclusion principle, what we have is, right, the last topic which we are going to study is Pauli's exclusion principle. Pauli's exclusion principle, what does it state? It states that this principle states that orbital can accommodate a maximum of 2 electrons and these must have opposite spins. Orbitals can accommodate maximum 2 electrons and they must be, they must have, and so this is related to the spin quantum number, wherein in spin quantum number, right, we have ms equal to plus 1 by 2 or minus 1 by 2. So this principle only states that. This principle thus limits the accommodation of electron in an orbital. This means that an orbit can have 0, 1 or 2 electrons. Moreover, if an orbit has 2 electrons, they must be of opposite sign, right? So this principle thus limits the accommodation of electrons in an orbital, right? This means that an orbital can have 0, 1, 2 electrons. Moreover, if an orbital has 2 electrons, So in this class, what we have seen about the we have seen about radial wave function. Then we have also studied the plots of radial wave function for different orbitals. Further, we studied about the probability distribution, probability density graph, that is chi-square graph, for different orbitals. Then we also derived an expression for radial probability function, and we plotted the radial probability distribution function as a distance of r. Then we also studied about the shapes of different orbitals, like s orbital, p orbital, and d orbital, right? We also studied about nodes. So nodes are basically regions of space where probability of finding an electron is zero. Then we also studied about the energy level diagram for an electron, right? Then we also studied about the electronic configuration of an atom, wherein we saw about this figure, right? So this is the order in which electrons get filled. Then at the end, we studied about three principles, which are the Pauli's exclusion principle, Afubov principle, and Hund's rule of maximum multiplicity. And with this, we cover the whole syllabus for this chapter, atomic structure, right? So I hope you have learned something in this lecture and in this tutorial series, and I hope you have enjoyed also. And I hope to see you again in the next class. Thank you.